Hey everyone, and welcome back to AI Paper Podcasts, where we do a deep dive into classic AI research papers. Today we're diving into Proximal Policy Optimization Algorithms, a paper from 2017 by OpenAI researchers.
It's a classic for sure.
And a good one. Even though it's from 2017, it's still super relevant today for reinforcement learning.
Yeah, the techniques they introduced are really fundamental to a lot of the progress we've seen in the field.
Absolutely. So for those who may not be familiar with it, this paper introduces a new family of policy gradient methods for reinforcement learning.
Right, and they called it PPO for short, Proximal Policy Optimization.
And it was kind of a game changer at the time because it addressed some limitations of existing methods.
Yeah, like think about deep Q learning.
Right, or those vanilla policy gradient methods.
Even TRPO, Trust Region Policy Optimization, they all have their issues.
Yeah, like TRPO could be really powerful, but also notoriously difficult to implement.
Totally. And it was super sensitive to the choice of hyperparameters.
So OpenAI really aimed to solve those problems with PPO.
And they did a pretty amazing job.
So let's break it down. First things first. Can you give us a quick refresher on policy optimization in general?
Sure. So in reinforcement learning, we're basically training an agent to make decisions in an environment, right?
To maximize some kind of reward.
Exactly. And in policy optimization methods, the agent learns a policy, which is basically a function that maps states to actions. So given a certain state in the environment, the policy tells the agent what action to take.
Okay, so it's like a set of rules the agent follows.
Exactly. And policy gradient methods specifically, they aim to directly optimize the parameters of this policy function.
So instead of like trying to estimate a value function like in Q learning,
we're directly tweaking the policy itself to make it better.
Got it. And how do they actually do that?
Well, it involves estimating something called the policy gradient,
which tells us how to change the policy parameters to improve performance.
Yeah. And to estimate that gradient, you need a stochastic policy.
Meaning a policy that has some randomness built into it.
Right. And an advantage function estimator.
Okay.
The advantage function basically tells you how much better an action is compared to the average action you could take in that state.
Interesting. So by combining these elements, we can figure out how to nudge the policy in the right direction.
Precisely. And the key to all this is the surrogate objective function.
Okay, that sounds important. What exactly is a surrogate objective function?
It's kind of like a stand-in for the actual performance metric we want to improve.
So instead of directly optimizing the actual reward the agent gets,
we optimize the surrogate function, which is hopefully a good approximation.
I see. And why do we need this surrogate objective?
Well, it turns out directly optimizing the actual reward can be really unstable and inefficient, especially when you have a complex policy with lots of parameters.
Ah, that makes sense. So this surrogate objective helps stabilize the learning process.
Exactly. But there's a catch. If you perform too many optimization steps on the same data using the surrogate objective,
you can end up with those really large and undesirable policy updates.
Right. Those updates can throw off your learning and make the policy worse instead of better.
That sounds like a problem. How do we prevent that?
That's where trust region methods like TRPO come in.
TRPO as in Trust Region Policy Optimization.
Yeah. The idea is to constrain the size of those policy updates to prevent them from becoming too drastic.
Okay. And how do they do that?
They use something called KL divergence.
Which is a way to measure the difference between two probability distributions.
Right. In this case, we're measuring the difference between the old policy and the new policy after an update.
So TRPO basically says, hey, you can update the policy, but only so much. The KL divergence between the old and new policy can't exceed a certain threshold.
Exactly. And that helps to keep the updates in check and stabilize the learning process.
Clever. But you mentioned earlier that TRPO had some downsides too, right?
It did. One major challenge was finding the right penalty coefficient for that KL divergence constraint.
So how much should we penalize large policy updates?
Right. It was this delicate balancing act. And if you chose the wrong coefficient, it could really mess up the learning.
So even with TRPO, things weren't perfect.
Nope. But that's where the PPO paper gets really interesting. They came up with this incredibly clever idea called the clipped surrogate objective.
Ooh, a cliffhanger.
We'll have to save that for after the break. Stay tuned. Welcome back, everyone. So before the break, we were talking about how TRPO had some limitations, right?
Yeah, like that tricky penalty coefficient for the KL divergence. It seemed like a real balancing act.
Right. You had to be careful not to constrain the policy updates too much or too little.
So how did PPO address that issue? You mentioned this clipped surrogate objective.
Exactly. It's actually a pretty elegant solution.
Okay, I'm intrigued. Lay it on me.
So instead of using a hard constraint on the KL divergence like TRPO does,
PPO uses this clipped objective to kind of gently nudge the policy updates in the right direction.
yeah. Imagine it like this. The clipped objective penalizes policy updates that move too far away from the old policy.
So it prevents those really drastic changes that could destabilize learning.
Right. But here's the cool part. It only penalizes those changes that actually make the objective worse.
So if the policy update actually leads to an improvement,
It gets a free pass.
that's pretty smart. So it encourages exploration, but in a safe and controlled way.
Exactly. It's like saying, hey, policy, you're free to explore, but don't go too crazy.
And how does this clipping actually work in practice?
They introduce this clipping function in the surrogate objective. So instead of just using the probability ratio of the new policy to the old policy,
They clip that ratio to a certain range.
yeah, it's like putting a cap on how much the policy can change in a single step.
Interesting. So it's kind of like a safety net that prevents those wild policy swings.
And this simple modification makes a huge difference in terms of stability and performance.
Okay, so that's the theory behind the clipped surrogate objective. But how did PPO actually perform in their experiments?
Well, they tested it on a variety of benchmark tasks, like continuous control problems using the Mujoko physics engine.
Mudoko, that's where you have those simulated robots trying to do flips and stuff.
Yeah, exactly. It's a great environment for testing reinforcement learning algorithms.
So they threw some pretty challenging tasks at PPO.
They did. And PPO consistently outperformed other algorithms like TRPO, A2C, and even vanilla policy gradients.
So it wasn't just a marginal improvement, it was a significant step forward.
Yeah. And what was particularly impressive was how well it scaled to high-dimensional continuous control problems.
Meaning tasks where the robot has lots of degrees of freedom and the action space is continuous.
Exactly.
Yeah.
Like controlling a humanoid robot with dozens of joints, PPO was able to handle those complex tasks with ease.
That's impressive. So PPO excelled in those continuous control tasks. Did they also test it on any discrete action spaces?
Oh yeah, of course. They tested it on the Atari learning environment, which is like the go-to benchmark for discrete action spaces.
Yeah, Atari games are notoriously challenging for reinforcement learning agents.
They are. But PPO managed to achieve comparable or even better performance than other state-of-the-art algorithms like A2C and ACR.
Wow, so it wasn't just a one-trick pony. It could handle both continuous and discrete action spaces.
And what's remarkable is that it achieved this while being simpler to implement than those other algorithms.
That's always a bonus. So it seems like PPO really hit that sweet spot of performance, stability, and ease of implementation.
It did. And that's why it's become such a popular and influential algorithm in the field.
But how did PPO change the reinforcement learning landscape? We'll get into that after a quick break. Welcome back to AI Paper Podcasts. We've spent the last two segments dissecting this groundbreaking paper on proximal policy optimization. But it's not just about understanding the technical nuts and bolts.
Yeah, definitely not. It's about seeing the bigger picture. Like, how has PPO really impacted the field of reinforcement learning?
Yeah, what's its legacy, so to speak?
Well, for one thing, it's made policy optimization much more accessible.
Okay, how so?
Before PPO, you had TRPO, which was, well, kind of a beast to implement.
Yeah. Right, super complex and finicky.
Exactly. PPO came along and simplified things. It made it easier for more people to use and experiment with these advanced policy optimization techniques.
So it democratized access in a way.
Yeah, and that led to a surge in new research and applications using PPO.
Makes sense. So more people could play around with it, push the boundaries.
And because PPO is so robust and efficient, it's been applied to a ton of different problems.
Not just those toy problems in a simulated environment.
No, we're talking real-world stuff like robotics, game playing, recommendation systems, even natural language processing.
Wow, that's pretty impressive reach.
And you know, this paper came out in 2017. That's like ages ago in AI time.
Right, things move so fast in this field.
But even after all these years, PPO is still going strong. Researchers have built upon the original ideas, creating all sorts of variations and extensions.
So it's like PPO spawned a whole family of algorithms.
Exactly. You've got PPO with different advantage estimators, different entropy bonuses, different ways to handle continuous action spaces. It's really amazing to see how much innovation this one paper sparked.
It's like the gift that keeps on giving. But no algorithm is perfect, right?
True. Even PPO has some limitations.
So where does it fall short? Where's the room for improvement?
One area is in dealing with really complex environments, especially those with sparse rewards.
Ah, that makes sense. Like where the agent doesn't get feedback very often.
Exactly. It can be really hard for PPO to learn effectively in those situations.
Because it's hard to figure out which actions were actually good.
Right. And another challenge is, well, hyperparameter tuning.
The age-old problem in machine learning.
It still takes some trial and error to find the optimal settings for PPO in different problems.
So there's still a bit of art to it.
There is. But hey, researchers are working on ways to automate that process, making it more user-friendly.
That would be a huge win. Make it easier for everyone to use.
Absolutely. But overall, PPO has been a game changer for reinforcement learning. It's paved the way for a lot of the progress we've seen in the field.
And it doesn't seem like it's going away anytime soon.
Nope, not at all. It's a solid foundation, and I'm excited to see what the future holds.
Me too. Well, that wraps up our deep dive into proximal policy optimization algorithms. If you want to learn more, we highly recommend checking out the original paper.
Yeah, it's a great read.
We'll include a link in the show notes. And as always, thanks for joining us on AI Paper Podcasts. Until next time, keep learning, keep exploring, and keep pushing the boundaries of AI.